We have our second speaker of the evening. His name is Zbigniew. He's going to be touching on deep learning, specifically in the context of scaling to the imagery. Z, yes, take it away.
Thank you. Thank you for having a chance to present a bit of my research that I was doing during my Ph.D. So my main interest lies always in applications. So here I try to discuss over these 20 minutes two of the projects that I worked on and may be relevant to some of the products potentially that some of you work. Unfortunately, not all of them for sure. So I always try to start with this simple small joke at the beginning of my presentation about like deep learning history. So in the 1960s, we had this first model of perceptron where it was able to recognize if on the photograph there is male or female, and we had like very simple linear model that took input x, multiplied it by weights, and used nonlinearity, a stepwise function to answer if this is male or female. And 20 years later, we have this beautiful model changed to a sigmoidal function, which is differentiable, and now we are able to update all the weights at single iteration, right? This is when backpropagation was kind of invented and allow us to much faster weight updates, which means much faster learning. And in 2000, we just discovered Rally, and this is what make our deep networks work, that the backpropagation doesn't vanish the gradients. So this is like 20 years of research actually that allow us to do the things that we can do nowadays. Obviously, it's a bit of job. But one project that I wanted to share is about upsampling. And this is done with my friends from Google, especially with Vittorio and Jasper, who are my direct supervisors in this context. So dense prediction problem are this kind of large set of problems in vision where you have to predict something per pixel. And we know all very well these successes from ImageNet, where recognition works very well on 1,000 classes and million images. But this is much more common in vision, that we have broad set of problems. And we mean about like semantic segmentation, about parts prediction, about instance segmentation, denoising, edge prediction, colorization, super resolution, depth prediction, surface normal prediction, etc., etc. So in our real life, the set of problems is much richer than ImageNet. But in context, this is like all the possible problems that I could come up that are popular in vision community. And typical architecture that is used for solution to these problems is we're using encoder, which is very well known from ImageNet, and there is a lot of them and a lot of research went into this part. We have like inception, exception, Resnet, Resnext, DenseNet, Polynet, etc., quite a lot of them. Then we start to upsample when we have like our high-dimensional representation, which is much smaller resolution. To get to the per pixel prediction, we need to somehow upsample it. And usually we do with this like encoder-decoder architecture and potential skip connection, where we process with 1x1 or 3x3 convolution and then somehow concat these two tensors together to recover the fine-grained details. So, as I said, like encoder, there was a lot of research actually about decoder. Yes, so these are like different encoders that are worth checking out depending on the application. But when we think about decoders, there is actually not too many of them. Magic Pony is one great example of a startup in London that was called that work on super resolution, and they apply sub-pixel convolutions to make it work better. There was also another research on depth prediction when they showed that 5x5 convolutions can be simulated in a faster way, and exactly the same equivalent operations by a set of 3x3, 2x3, 3x2, and 2x2 convolutions. So that was nice, but in my opinion, it's actually not too broad research in this context. One actually of these three examples that researched this decoder part was about checkerboard artifacts. So if we look at the GANs, we may see that they have like this weird effect of like checkerboard artifacts, where like values are flipping higher, lower when we like move along the axis. And this is actually just because of the upsampling method that we use. This is nothing to do with like GAN laws or specific encoder architecture or like this architecture of the discriminator. It's much more about like the upsampling in the generator. And I will explain in a second why this happens. So I tried to make this relatively large-scale study of 6 different problems, 2 that require classification per pixel, 2 that require regression per pixel, and 2 that require kind of pixel generation in super resolution and GANs, and try to analyze different upsampling methods and decoding to kind of make some consistent conclusion. What's the best way if you are building your own model in your company or in your research project, and you want to start from something that's very decent, and you don't want to worry that you screwed something in this part because you are researching a totally different part of the model. So how transposed convolution work is actually kind of like inverse operation to convolution in the sense of like dependencies on the pixel values. So obviously inverse operation to convolutions is ill-defined, but the dependencies are very well defined. And if we do 3x3 convolution, so for this, let's say for this 3x3 box, we would generate this one pixel. So in the transposed convolution, from this one pixel, we kind of try to generate this thing. But because we have start 2, this is equivalent to actually filling zeros in between these pixels and applying 3x3 convolution on top of it. That's exactly what transposed convolution is doing. And this is a very common way of upsampling in all our models. So the obvious drawback of this method is that it must have the checkerboard artifacts, because if you see what's happening with this 3x3 convolution applied on this map, is that this pixel generated in the next layer will be dependent on 4 different values, and this pixel will be only dependent on the single value. So there must appear these checkerboard artifacts. And similar story is with like depth to space or subpixel convolution, when we shuffle the location-based pixel into space by just putting them next to each other, and in this way we can create something of higher resolution. But unfortunately, we also see then this like jumping of values. So bilinear upsampling is nice in this context because it allows us to do it smoothly. So like generated pixels will be some sort of approximation or interpolation between the 2 pixels from the lower resolution layer. But the drawback of bilinear upsampling is that we actually artificially inflate the size of our tensor. We go from like HW, which is height, width, and depth, to something that is 2H and 2W, 4 times bigger, and we don't really create any new information. And we have to spend more time on computing and potentially overfit. So it's in this context, it's not the perfect setup, but it's better than having these checkerboard artifacts in few use cases. So we come up with something that we think is even better than this, which we call bilinear additive upsampling. So this is idea similar to depth to space, but we want to do this in the smooth way. So what we do, we first say, okay, we upsample by bilinear upsampling, and then we add every 4 channels together. So going from HWT to the tensor of the same size, so like the representation of our input image in number of floats is the same. We don't inflate, we don't do bottleneck in the across the architectures, but we have now a smooth way to do upsampling of the features. And because of this, it doesn't have any intermediate operation, any convolution or anything like this. So we can think about it as some sort of identity for upsampling. Because we couldn't have identity before because we needed something of bigger resolution. So thanks to this layer, we can now define residual layer for upsampling. So some sort of like residual connection in Resnet. And we know that residual connection is useful for simplified training, and it trains faster, and it allows for the flow of the gradient easier. So with these tricks, we compared on all these 6 problems, and here are some results. So we see that depending on the type of convolution that we use, so we tried transposed, decomposed, transposed, separable convolution, bilinear upsampling, sublinear, and this our proposed method bilinear additive upsampling. So we see that there is kind of high variance in different methods across different problems, and it was difficult to define one single upsampling method that would be like very robust. So if we compare what's happening when we add residual connection by this additive linear upsampling, we actually get something to do what is much nicer. The red color means better results. So in general, we kind of omit the problematic, most of the problematic models. And this is what is actually kind of important when you start with the new problem, to start from the model that works. It doesn't have to be state-of-the-art, but is training well and gives reasonable results. And if we try to find out like which model is kind of the best across the lowest performance across all the 5 problems, bilinear additive upsampling gives the best overall results, even though it may not be the best across all the methods for the given problem. Across all the problems, it's the most robust method. And I think what is really exciting is that the performance, especially for these generator-based tasks, is much higher. So if we look at the super resolution and GANs, which are quite popular right now, we see that there is at least 10% improvement in all the GANs implementations. So to give you some sort of qualitative example, this is how the depth prediction works in context of 3 layers that have potential for checkerboard artifacts. Transposed convolution, you can see clear crosses in depth to space, especially on this image. You also see the checkerboard artifacts, but with our additive bilinear upsampling, it's much smoother. So I think this is some feature of the network that you would like to have in your applications. And this is okay. Maybe don't go into this. So that's first project, and this layer will be, it's still not yet checked in the TensorFlow code, but it will be checked in very soon. And the second project, which is a bit older, about the transcription of the street view images for the street names, is actually fully open source in TensorFlow under TensorFlow models OCR. So if you have a problem where you have to transcribe text in the kind of natural scenes or not very long texts, it's actually the best model to use. And this is also a project with my friends from Google Street View team. The deep learning for Street View is called StreetSmart, and with Kevin Murphy. So this is the problem. We have a few shots of different signs, and we want to transcribe it. And what's interesting, this is an example where our model was correct, even though the transcription was wrong. So it had like the better French prior than the person that generated the labels. Sometimes we have few shots of the street signs, sometimes we have only 2, we can have only 1. Sometimes these shots that don't match each other. And this data set is open source, it's called Street. So quite simple name. It's around 1 million like shots of the 4 up to 4. So it's relatively big, but it trains on single GPU in probably less than 2 days. So here are some examples where our model was wrong in the last 2. So like different font confused the model, and the mold, the dirt on the sign also confused the model. But in the case where it has to predict some sort of structured information, like omit the numbers, for example, or like extend the abbreviation, it was able to do this even though some letters don't appear on the sign.
Yeah, why do we need 4 views of the training data set here?
Sorry?
So for each training sample, we are taking 4 views, right?
Yes,
Yeah.
so this is specific of the data set. So this is how it was published, and we always in research try to benchmark with respect to data set because we work on the model. If you think about like real use application, obviously you can, you define the data set, right? If you think about your company, then it's not relevant. But this is how it was constructed. So what we do, we use standard attention in this context. Maybe what is not super standard is that we do few embeddings that are not in every implementation. So we process our shots with part of the inception, so we cut it after 14 layers. Inception is very efficient network. It has the group convolution, which allows for much faster processing, up to 3 times, for example. But we don't want to predict, cuts, faces, cakes. So we don't need so many layers, and it's enough to cut on just few layers, and it works really well for text as well. So after this, we use attention mechanism, which define the attention masks. Attention mask is a probability mask over the downsample 2D representation of the processed image to define which pixels will be taken to prediction of the next character. And based on this attention mask, we multiply by these tensor features, and we sum them up with respect to the width and height, and then we get one by one vector of a number of the size of number of channels, and we use this number of channels to predict the next character that the model tries to recognize. And to generate this attention mask, we use the previous state from LSTM. So this is kind of, if it's a little bit sophisticated, if it comes to the explanation on one slide, but this is standard attention mechanism. So we have comparison to generate this attention mask. We just compare them with the query from the LSTM with every pixel, and if the dot product between these two is high, then we assume that this pixel is actually contributing a lot to the next character prediction. And what is maybe not fully in every attention model is that we do here like one additional embedding, which is just one linear layer on every feature map, and we do the same embeddings when we predict the characters. And it's maybe, it seems like a simple thing, but it's worth having this in your model if you work with attention. So therefore I recommend this implementation of this mechanism. And trick that we introduce in this paper is about like adding coordinate encoding cues to character prediction, because we know that our attention mask should go step by step, in the sense that if we predict the character A and the next is B, we should like look at the location where the B is. And with attention mechanism by default, like all these high-dimensional pixels are kind of independent, so they could be shuffled, and mathematically it's exactly the same model because it's compared with the dot product from the query that comes from LSTM. So in this way we could like some sort of encode the coordinate, and model could learn that, okay, if we look at coordinate third, then we should look for the pixels that are on the coordinate 4, because we read like sequentially. And with here is comparison of different cuts in inception, and with this coordinate, one-hot coordinate encoding, we have around 1% improvement in our model. Most of the actually errors are coming from the wrong ground truth, but some of them could be still probably improved with, for example, beam search. This is one of the ideas that we didn't have time to explore and should help in maybe 1, 2, 3%, we don't know. And here is actually a nice comparison. We compare green, which is attention mask from attention mechanism, and we compare the red, which is saliency map. So saliency map is the gradient when we try to predict the correct character, and we compute the gradients up to the input image. So then red means more or less how much the given pixel contributes to the prediction of the current character. And we see that in the first glimpse of the model, it actually recognized the whole world, because there is only few starting names of the street in France. It's like Rue, Ruelle, Avenue, Avenido, Place, etc. It's maybe 10 of them. So it doesn't read like character by character. So it has like this prior, on the left-hand side of the shot to kind of don't read anything in the current step, and it just like predicts characters based on LSTM state. And when we get to the point that characters actually change quite a lot, we see that these green start to overlap nicely with the red saliency maps. So this is kind of interesting to see how model learns to read and how this compares with our intuition. And actually what is interesting, we've seen this trick in the also working in the business name prediction, even though we don't give like a very narrow shot. So here the name is Zelina Pneus, and model was able to recognize that Bridgestone and Firestone, because they appear quite often, they are not business names. So it was able to predict Zelina Pneus based on around like 400K images of such business fronts. And this is like the same mask for business names. And here we can see something actually what is really nice. I really like this example because here we have like the name of the business in two places. One is quite large, and this is where humans usually start reading, Lambert's tire service, but model actually prefers to read from this part, which is like smaller fonts, but is more standard font. So it's easier for her to read these characters. And this is something that we are currently actually developing in TensorFlight, which is like end-to-end transcription and detection for our business, for analysis of the buildings from street view type imagery for the insurance companies. Yeah. We also had like one work that actually was not published, so it seems like it's not the best idea because we couldn't beat the state-of-the-art results. It's about like doing instance segmentation by pixel embeddings. So every pixel have like own embedding, kind of like word2vec, but for pixels. And if the pixels, are placed in the similar location in this embedding space, they're supposed to mean the same instance. But this is like projection, 3D projection of these pixel embeddings, but unfortunately we cannot really beat the state-of-the-art results from Facebook, for example. So yeah, it's rather not the best way to go. And I also work on inception and object detection, but I think I wouldn't like to go into these details right now. It's kind of story. Oh, actually, yeah, 2 minutes. If anyone is interested in medical applications, there is a group at UCL that I also collaborating. There is Khan here at the end. So we used to work on this digital mammography cancer detection. So we have like these huge images, 4,000 by 4,000, and we try to predict is it cancerous or not. And what is interesting, usually on ImageNet we have like 2 to 4 by 2 to 4 and try to predict 1,000 classes. Here we have like 4,000 by 4,000 and try to predict 1 or 0. So it's not really feasible to make it with just simple classification. And the main idea is just to try to gather as much detailed information as possible and use models that can process as big imagery as possible. So here is the first time I actually trained models that were of size 2,500 but 2,500. So this is usually batch size 1. You cannot benefit from batch normalization because the batch is only 1. But the bigger the image, usually the better results you get. So this is kind of like simple answer. And VGG was the model that got like the first place. VGG with detection model got the first place, while VGG is very old and expensive model, but actually it consumes not too much memory because it doesn't have any batch normalization layer. It's just 5-6 layers of 3x3 convolutions, and therefore it's quite efficient in terms of memory. And this is why it's also worth thinking about having this in mind. So the cancer that you try to find is actually like 1 less than promille of the image. So it's difficult, interesting problem. So if anyone is interested, obviously there is a group at UCL that is very engaged in this project, and probably a few more will start as well in medical imaging space. And obviously we also try to do pre-trained models, and pre-trained models usually helps. So that's even though it was pre-trained on ImageNet, but the features that it was learned, it can be treated as features that have good initialization. And extra bonus, I'm currently developing artificial intelligence for property inspection. The main point is that insurance and reinsurance companies, they have to evaluate policies when they get the quote, and for reinsurance companies, which get like huge quotes of 50, 100k buildings at once, they don't know anything about half of these buildings. That's the case from US. And if we could provide few highly correlated features with the risk related to insuring the property, this is very valuable information to them. So if anyone is interested in this project, also please chat with us. So we look at the kind of aerial, satellite, street view, and oblique imagery and try to predict different features.
2 minutes.
2 minutes, okay. So actually I'm finishing here. So some features that are relevant is like, okay, like what is the roof type, what is the roof slope, do you have swimming pool? Because if you have swimming pool, it's more expensive policy because there is bigger chance that you will have accident, and these kind of things are very important for the insurance. So this is some models that work in our system. So we have to process like huge images, and yes, we're always interested in research collaboration and also in like contracts with insurance and reinsurance especially. These are like few ships at the end. Thank you.
Dave, once again, we'll take a couple of questions before we poll our speakers at the end. Yes, shout out. Can you give us your name and where you are?
Hi, I'm Jacob. I'm working in data science consultancy. So I just asked you, like you to ask comment on go back to the first bit of your working on like Transposed Convolution. So one is there was a recent paper from NVIDIA about progressive growing of GANs, and then generated full HD images that didn't seem to suffer from this problem. I think they use some sort of residual component, but why do you think that hasn't happened to them? And I just had a question around, so I love that you cited are all GANs created equal study, because I think that that's like a really important one when it comes to generative networks. But so one of the big conclusions for me from that paper was like computational budget methods, right? Like you shouldn't just throw computational resources because then every GAN is going to get to a particular performance, right? But you introduced a learned embedding, and how much computational complexity is that adding? So if we were to compare like your results with a fixed computational budget, would that change? Because obviously that introduces an extra layer of computation and optimization into the system over and above the regular GAN. So how would that change?
Thank you for questions, because it was very long. So the first one was, let me answer the second one. So GANs created equal is a very nice paper because they throw a lot of GPUs, because they are in Google, so they can a lot of GPUs on this problem. And what we see that the hyperparameters matters much more than really the loss function. And I kind of believe in this. Maybe there are like two losses that try to stand out. So in our experiments, if you think about residual connection, there is identity connection which doesn't actually introduce any computation. You only have to do bilinear upsampling. And this is what we claim success here, because we only introduce this bilinear upsampling and adding like the channels and summing this up, right? And nothing more, which means like we introduce zero new parameters and a little bit of the computation, because we only have to do bilinear upsampling. And with this trick, we got like improvements on the 10%, which is a lot. With respect to progressive GANs, this is different architectures. Progressive GANs are going to be at iClear. Our work was submitted to IJCV from as a special edition of IJCV, which means it's not yet published even. So we are kind of like starting from slightly different model. It was architecture from InfoGAN. We say, okay, here is architecture of InfoGAN. We are using Wasserstein improved gradients or improved loss with gradient penalty. We use these two things, and now we compare different ways of upsampling. Because they use transposed convolution, but we tried also like few others, and we also add our own. And we see that our identity connection in terms of upsampling, so this like identity as we defined it, actually helps quite a bit, and no new parameters. So I think it's kind of strong results. Obviously, progressive GAN currently have better results, but comparing to our baseline, we have improvements. So if the arracher, if the reviewers will argue with us, then we will have to go to progressive GAN, implement it, and show that our results actually improve also progressive GAN. But I don't think this matters much from the research perspective.
One more? Do we have one more question for Zeke? Yes.
Hi, I'm Takuya. I'm an independent consultant. For the property insurance project, you showed us who owns those data of the property, who really owns the property, those data. I mean, because you need to analyze the data.
Yes, we have to buy the data.
You have to buy it?
Yes.
Ah, right, okay. So it's not the case. I mean, I feel personally uncomfortable if you can analyze my house, for example, getting those data and handing to the insurance. So I'm just curious of who you access to those data.
Throwing you an ethical curveball. What if I was to use a drone to capture that imagery?
I mean, obviously there are a lot of regulations, especially in the US, around drones. So we started our journey with TensorFlight with respect to drone business, but like we closed the drones in the last summer because of regulations, because of the amount of imagery it's collected, we don't see there like huge opportunity. And with respect to the ethical question, I mean, it's anyway happening, right? Like insurance companies and like credit companies are scoring every person when they try to like predict if this person should get the credit or how much the policy should cost them. And if someone is trying to insure their home and they don't have this information, that's probably they are going rather assume worse than better, right? So if they have this information, they actually can insure your house cheaper because they are confident that this is not a totally screwed house and the roof is in a good shape, etc., etc.
You wonder why bomb builders live in volcanoes. Thank you very much.